Hello students, today class will discuss about the crystal field stabilization energy, how to calculate crystal field stabilization energy in octahedral complexes. As we know, in octahedral complexes, the d orbitals of central metal cation are split into two sets of different energy levels, right? The energy difference between these two sets are said to be delta O, that is a octahedral crystal field stabilization energy, which is further equals to 10 d cube, right? This is also can be written as 10 d cube. So now in another verse we can say that 3 of the d orbitals are here out of 5, 3 of the d orbitals are stabilized by the value of minus 0.4 delta O, and the remaining 2 of the d orbitals are destabilized by 0.6 delta O. These 2 orbitals are destabilized and these 3 orbitals are stabilized, each electron present in the orbitals, right? So let's see how to calculate the crystal field stabilization energy for D1 to D10 configuration. If it is only one electron is present, that means the electron invariably it will enter into the TTC level. So each electron will contribute, that is minus 0.4, and it is having one electron. So the total delta O value stabilization energy equals to minus 0.4, which is same as in the strong field also. There is no further electrons in the strong field to get paired up. So the value is same for T2C1 weak field as well as strong field. And D1, D2, D3 configuration, the weak field and strong field used to have same CFSE value. The reason here is, according to the Hertz degeneracy, once the electron field completely singly, then only it will get paired up in the case of degenerate orbitals. That's why up to T2C1, T2C2, T2C3, there will be no contribution of pairing energy. The CFSE is the total contribution of delta O only octahedral. So let's see the D4 configuration. In the case of D4, there is a difference between strong field and weak field. But suppose if it is a strong field, that means greater will be the splitting, greater is the delta O value. So as the value energy difference T2C and EC is very high, the electron cannot jump from T2C to EC. So the fourth electron will enter in T2C level itself. So there is a one pair of electrons are present, one pairing energy also there, and the total electrons present in T2C will become as T2C4 in the case of strong field, whereas weak field it is opposite. Weak field the difference is very low, so electron can easily jump from T2C to EC level. So T2C3 and EC1. So for the weak field you will write T2C3 EC1, whereas strong field you will write all the electrons are entering into the T2C4. So the CFSE value is going to vary from D4 to D7 configurations, weak field and strong field. Next, move to the D8 and D9, D10 configuration. For these three particular configurations, the CFSE value and the pairing energy will become same for weak field and as well as strong field. The reason here is, in the case of D8, the electrons will first enter, whether it is weak field or strong field, it will be completely filled, that is a T2C6, and whereas EC is having only 2 electrons. So even it is strong field T2C6 and EC2, even it is weak field T2C3 and EC2, again it will come to the T2C. So there is a no difference. So that's why the value is same for weak field and strong field in the case of D8, D9, D10. So let us look for the questions, what kind of questions used to come from this concept. So first question, which of the DN configuration, electronic configuration are having highest pairing energy? So the pairing energy is nothing but, here you see the CFSE, crystal field stabilization energy, can be calculated, the total contribution of delta O plus MP. So here what does mean by P here? P means the electrons present in the T2C level, Q means the electrons present in the EC level, whereas the MP, M means what here? The total number of pairs of electrons present in both T2C and EC level. So let us look for the question here. They are asking about which configuration used to have highest pairing energy. So first they have given D10 high spin and D8 low spin, D10 low spin. Let us look for the D10 high spin. As I said earlier, the D10 low spin and high spin both are having delta O value is same, 0, right? So, and this is a 0. And if you look at T2C6 and EZ4, here you see T2C6 and EZ4. 4 means easy level, 4 electrons are there. So all the electrons are in the form of paired. So that means total it is having how much pairing energy? Plus 5p. So the highest pairing energy you will observe in the case of D10. So option D will be the right answer. The next question, if the delta O and delta T is denoted respectively, that is octahedral crystal field splitting and tetrahedral crystal field splitting, then what about the ratio between delta O and delta T? So as we know how it was interrelated actually, delta O you can also written as, see here, delta O, and delta T you can also written as 0.45 delta O. That means you could replace the delta O value, delta O upon delta T value, you can replace it as 0.45 delta O. That means 1 upon 0.45, which is equals to 2.2. Option C. And if they are asking, suppose calculate the CFSE value for hexaamine cobalt plus 2 complex. Cobalt configuration is D7 4s2 as it is in plus 2 D7. So as a D7, ammonia is acting as a strong field ligand in the case of cobalt. So the electrons in D7 can be filled up as a T2C6 and EZ1. Each T2C electron is contributing, that is delta value minus 0.4 multiply with 6 plus 0.6 multiply with 1. So the total value is equals to 2.4 plus 0.6. Okay, so which is further equals to minus 1.8. This is about delta O value, octahedral. And here you could also observe at the same time all the T2C electrons are in the form of pair. So plus 3 pairing energy, 3p. So overall CFSE value is the addition of minus 1.8 delta O plus 3p. So in this way you have to calculate. Next, for the hexa-aqua chromium plus 2 complex, they are asking about pairing energy is found to be, they have given the value of pairing energy, that is 23,500 inverse centimeter, and the magnitude of delta O, that is octahedral crystal field stabilization energy, also given, that is 13,900. Asking to you to calculate the CFSE for both high spin and low spin. First consider chromium plus 2 complex is D4 configuration. D4 configuration high spin we are considering. High spin means weak field ligand. For the weak field ligand there is no pairing energy. There will be no T2Z and EZ gap is very high. There is no possibility of electrons will get paired up here. So here all the 4 electrons, first 1, 2, 3, 4th electron will enter into the EZ level. So is it having any pairing? M electrons? No. So 0. M value is 0. But the value is given 0.6 delta O value. They have already given the delta O value as 13,900. If you substitute 13,900 value, 0 pairing energy will get it as minus 8,340 values, right, inverse centimeter. But whereas in the case of low spin means strong field ligand. Strong field ligand, all the 4 electrons will enter into the T2C level itself, right? So T2C level means 1, 2, 3, 4. There is one pairing energy also there rather than delta O. We can substitute same value, that is a minus 1.6. 1.6 why? Because all are contribution of T2C's electrons. Each electron minus 0.4 multiply with 4 electrons, so 1.6. And delta O value has given, that is 13,900 plus 1 pairing energy. So here P value has given, that is 23,500. If we substitute this value, we will get exactly 1,260 inverse centimeter. If you observe both cases, which one is having high CFSE value? This one, right? This is positive 1,260. So that was the reason the low spin chromium complex is more stable compared to the high spin chromium complex. So these are the strong field ligand chromium complexes are more stable compared to the high spin complexes. So in this way the questions used to come. The another question here, they have given two complexes data, that is hexa aqua manganese complex and hexa aqua rhenium complex, and they have given the data of delta O value and as well as pairing energy value. From the above data, first you see manganese plus 3 and rhenium plus 3. Both manganese plus 3 and rhenium plus 3 are having configuration that is D4 common. So both are having D4, but the principal quantum number is differ. But let's see, configuration is same. So D4. But the CFSE, how it is going to vary? Let's see. For the CFSE value, how we can calculate. CFSE value has given, that is for a manganese complex they have already given, that is a 250, and whereas the rhenium complex they have given in the data, that is 400, right? It has already given in the question. So which is having CFSE, greater CFSE in the case of rhenium? That means the difference between T2C and EZ is very high in the case of rhenium compared to the manganese, right? This difference is very high. So automatically the pairing energy is very low here. You could see here. Here the pairing energy has given very low compared to the CFSE. So automatically the electrons are tries to enter and get paired up here itself. 1, 2, 3, 4. As it is very high, electron cannot jump into the T2C to EZ level. But whereas in the case of manganese, what is happening? The T2C and EZ difference is very low, as they have given CFSE lower compared to the rhenium. So after 3 electrons filled in T2C level, the 4th electron tries to enter in EZ level. So the pairing energy is very high. So the pairing is not possible here. That means these are actually high spin complexes, whereas rhenium is low spin complex. So here what they have given options, the manganese is low spin. Is manganese not low spin, high spin? Because the difference is low, so electron can jump here. So the pairing energy is very high. So but it is a high spin complex, whereas rhenium is low spin complex because it is pairing energy is very low. That's why it can get paired up easily in the T2C level itself. So thanks for watching this video.